In this video, we're going to talk about two things: new functions from old functions, as well as power functions. And so we've already talked about linear functions, exponential functions, and logarithmic functions. Now we're going to look at more algebraic type functions. And one thing about algebraic type functions is that you can combine them in different ways. And based off of the ways that you combine them, you can create more complicated functions, right? And one way to combine these functions is to look at what we call power functions. You're looking at composite functions, right? And so this says if f and g are functions, the composite function f, that's a little circle almost in the middle, like a multiplication symbol with a g, that's denoted, that's the denotation or the notation for f composed with g. And it is defined by f composed with g of x is f of g of x. And so basically, remember when we're talking about functions, we're talking about inputs and outputs. And basically what we're saying here is that when we write this notation f of g of x, our input value x is going to be coming from a set called our domain. So we have a bunch of x's here. We apply our rule g, our function g to that first, and then we'll get a set of g of x's, as long as x is defined by this rule. And then we take those g of x's and we place it inside or apply the function f of x to that, and we end up with f of g of x. And so it's kind of like a step-by-step thing. We apply the function g first, and then we get some g of x's. We apply our function f to that last, and what we end up with is what we get if we knew the formula for the composite here. We get f of g of x. All right, I know that looks like fog, but that's a little open circle between f and g, right? And so we wanted to be able to look at when functions are combined in this manner. We also want to be able to look at when functions are added, subtracted, multiplied, and divided by each other, because when we get to calculus, those combinations require us to do different things in reference to calculus. And so let's look at a couple of examples of getting used to this notation here. It says let f of x equal x plus 1 and g of x equal x squared. Find the following, right? We're going to do f of g of 2, right? Well, what this means is go to your function g and substitute 2 in for x. And so when I do that, I have f of basically 2 squared, which is 4. And then I replace this 4 inside of my function f, wherever I see an x, and I get 4 plus 1, which equals 5. All right. G of f of 1, well, we go to our function f and put 1 in for x, and we get 1 plus 1, which is 2. And once we do that, we go to our function g, plug in 2, and we get 4. All right. And so we can come up with a formula for this, and then we could have also done this way using the formula. And so sometimes you'll want to calculate the formula or figure out what the formula is for your composite function, and then you can substitute it at values as well, right? For instance, f of g of x, that means we're going to replace x in our function f with the formula for g, right? So my formula for g is x squared, so I just replace this g of x with x squared. And basically this says to go to my function f, and wherever I see my variable, input the value x squared, right? And so since it's an x plus 1, instead of writing x plus 1, now I'm going to input an x squared there. So I'm going to get x squared plus 1. We'll do a similar thing, but in the opposite direction. We go to our function f, and what I'm going to do is I'm going to take the formula for f, which is x plus 1, and I'm going to replace it in my function g wherever I see an x, and there's only one x there, which is squared. So instead of writing x squared, I'm going to write x plus 1 quantity squared, and that's what that equals. And so we could revisit these examples here, right? Since I know f of g of x is the same thing as x squared plus 1, so if I want to do f of g of 2, all I have to do is go here and plug in 2 for x. I get 2 squared plus 1, which is 5, right? So having this formula means that I don't have to go do this step by step. Now I have a formula, I can put it in one step. All right. The same thing happens here for g of f of 1. That's a parenthesis there, g of f of 1. If I plug in 1 into my composite function, now that I know the formula for it, that'll be a 1 plus 1 quantity squared, which will give me a 4, right? And so there's value in having the composite function, but there we go. Let's look at this example where we have a table of values. Remember, we can represent numbers using the, or anything mathematically using the rule of 4, right? Numerically, verbally, analytically, and graphically. This is numerically looking at a table. Finding f of g of 2, right? This means I go to my table with my function g, find out when the input value is 2. My input value is 2 here for my function g, and the output value is 4. So g of 2 is the same thing as 4. Now I need to find f of 4, so I go to my table with 4 and get the output value there. That equals 1. Part B, I have g of f of 3. So this says, oh, when your input value is 3, what's your functional value? Oh, that is also 3, so I get g of 3. And then I go to my function g, find out the x equals 3 and give the output, which is 1. You can do a composite of the function with itself. So f composed with f evaluated at 4. So I go to 4. For x, find the output, which is 1. So this reduces to finding f of 1. And then I go to 1 with my same table with my function f, find the output, and I get 4. So I get the same thing I started with. G of 2. Well, I go to my function, my table with my function g, find out the x value 2, find the x value 2, and get the output value, which is 4. So this would be the same thing as g of 4 because g of 2 is 4. And then now all I have to do is find g of 4. So I go to my table, look at where my x value is 4, and give the output there, which is 0. All right, so this is the inner workings of these composite functions or compositions of two functions. You can actually do compositions of more than two functions. We usually don't do that very often, but it is possible. Let's look at being able to determine which function is an inside and outside function when we look at composite functions. So in this notation, g of x, this function that is applying to our input variable first, that's what we're calling our inside function. And then f of x, which is done last, is our outside function. And the words inside and outside are going to make a little more sense once we start getting into how these things look here, right? So it says find the inside function, which we're going to call g of x, and the outside function f of x in the following expressions. Notice here in part A, I have the quantity 3x plus 2 in parentheses. That's why I say the quantity, and that's squared, right? So what we want to do is look at what's done first to the variable, and then what's done second or overall or last, right? The first thing that's done is inside the parentheses, right? The 3x plus 2, right? First, the 3 is multiplied by the x, then the 2 is added. And then lastly, everything is squared. And so if I were to pick an inside and an outside function, remember we're calling g of x our inside function, f of x our outside function, then my inside function would be 3x plus 2. Notice the inside of the parentheses. And the outside function is what we do to that inside function. All right, now what we're doing to this inside function here is squaring it. So my outside function is just a variable squared, all right? Now we can check ourselves by doing the composite or the by doing the composition of functions. Really, I can't talk today. And so what I'm going to do here is I'm going to check myself. I'm going to put g of x in first, right? So I have f of, well, the expression for g of x goes there. And then I replace that in my function f wherever I see an x, which is that squared term. And so I get a 3x plus 2 quantity squared. And that is the same thing that I have here. So I did pick the inside and the outside function correctly. Let's go to part B here. I have the natural log of x plus 1, right? So I got to think about what's done overall and what that overall thing is done to, right? Notice I have a natural log of the x plus 1. Now my variable is in that parenthesis with x plus 1. So that's a good sign that x plus 1 is going to be my inside function. Notice again, it's inside parentheses, right? And the thing that I do to the x plus 1 will be my outside function. And since I'm taking the natural log of it, when you write your outside function, you do the natural log of just a variable. because that's what you're doing to the inside function. Again, you can check yourself. When you check yourself, all you're going to do is you're going to plug in this x plus 1 in for x here, and you'll see that you get the same thing you started with. Let's go to part C, which doesn't have a parenthesis, right? So these are kind of simple because you can see the inside function is inside parentheses, but this one doesn't have a parenthesis, and I want to look at this one. All right. And so I have e to the 2x, right? Well, my x is in the exponent with that e of that e, and it's multiplied by 2, right? That is what is done most immediately to my variable, right? 2x. And that is an exponent on my e, or my natural exponential function. And so what I would use as my inside function is 2x, because that is what's in the exponent of e, so I use my outside function as e to the x. Now, this one probably requires you to check yourself, all right? And so I'm going to do f of g of x. So my g of x is 2x. So I replace g of x here with 2x. And then I'm going to go wherever I see a 2x in my function f of x, I'm going to replace it with 2x. Well, I only see it in the exponent of the e, so there we go. We have our solution there, all right? There is another way that we can do this one, all right? And I want you to try to figure out another way to do this one here. Find another g of x and f of x that works as your inside function and outside function other than the one that we had here, and we'll talk about it in class. All right, so that's composite functions, doing a composition of functions. All right, let's go to what we call power functions. Power functions, if y is proportional to a constant power of x, then it is called a power function. What in the world does proportional mean? All right, in math, proportional means that when something is related to something proportionally, one thing is some number times something else, right? So when it says y is proportional to a constant power of x, that means you can write your output value y, which we're calling q of x here, equals some constant, which we're calling k, times x to some power, right? So p is your power or your exponent, whichever one you want to use. We're going to use power because these are called power functions. And k is a constant, right? We call that the constant of proportionality. All right, that shouldn't be a period there, but oh well. So any function that can be written as some number times x to some power is called a power function. For instance, 3x squared is a power function. 2x to the 1/2 is a power function. 18x to the -3 is a power function because it's some number times your variable raised to some exponent. Power function, all right? So we're going to look at some examples here and determine if they're power functions. And if they are power functions, we're going to identify k and p, right? So basically, can you write these functions as some number times your x to some power, right? And in this example here, we could write this. Anytime we divide by 9, that's the same thing as multiplying by 1/9, right? So we could write this as 1/9 x to the 10th. And so this would be a power function, because k would in this case would be 1/9 and p in this case would be 10, right? So we do have a power function in part A. Let's go to part B here. We have a variable in the denominator. Well, whenever you have a variable in a denominator, there's a rule of exponent that says, okay, well, 1 over x to the n is the same thing as x to the negative n. That's a power or rule of exponents. You call it the reciprocal rule. So if I don't want something to be in my denominator, then I can bring it out of my denominator into not being in my denominator by doing the opposite exponent. So since that's a +4, this can be written as 2/7 times x to the -4th power. So here my k would be 2/7 and my p would be -4. So yes, it is a power function. All right. Let's go to part C here. We have some other rules of exponents to use. And actually, this is the definition from algebra. We always want to remember that when I have some number to the m over n power, that is equivalent to saying that this is the nth root of that base to the nth power, right? So the n, as in Nancy, is the index on that radical. Like, so if it was a square root, it would be 2. If it's a cube root, that n would be 3, right? Fourth root, fifth root. So the denominator of this fraction is your index, and then the numerator of this fraction, the top part, is the exponent there, right? And so what we can do here to see whether this is a power function or not is we can rewrite it as a fractional exponent, right? That's a 2 as my numerator and a 3 as my denominator if I change it to a fractional exponent. So that's x to the 2/3 power. Well, that's in the denominator. So I could write this, take it out of the denominator, and so that it's no longer in the denominator, and negate that exponent. And now I can write this way. And again, that was using this rule here. And so yes, this is a power function because k, my constant of proportionality, is 3, and p is negative 2/3. So that's a power function. And now we go to part D here. I have y equals 4 to the x. Well, power functions have x as your variable raised to a power. Here, this is a number raised to a variable. This is not a power function. It's actually a function that we've already, not a power function, it is a function. It's not a power function, it is actually an exponential function. Exponential functions are not power functions. All right, I say stuff, it's an exponential function. So there's no k and p to look at here. That's not a power function. All right. And so power functions are pretty cool because they have graphs that we can use in calculus, right? These graphs are smooth and continuous. These graphs are smooth and continuous for some values of your x, your input value, right? So since they're smooth and continuous, they have good properties that we can use in calculus. That is why we're going over them. All right, some of the most popular power functions, well, when we combine certain types of power functions, we can come up with what we call polynomial functions, right? And so polynomials, all right, we don't have the definition here. I'm going to type the definition over here. You may not have any room on your paper if you printed my notes out, but I'm going to say polynomial functions. If I can get it right. Polynomial functions involve the sum of power functions with whole number exponents. All right, so polynomial functions have whole number exponents. Now, by whole numbers, you got to remember your sets of numbers, right? Whole numbers are numbers such as 0, 1, 2, 3, 4, 5, right? So you can't have negative exponents and you can't have fractional or irrational, rational or irrational exponents, right? Fractional, right? So if it's a polynomial, it's going to be a sum of power functions where p is a whole number, and a whole number is 0, 1, 2, 3, 4, 5. Okay? And so an example of a power function or polynomial is y equals 3x squared plus 2x minus 1. Notice this is a power function, this is a power function, this is a power function, right? This is x to the second power, which is a whole number. This is x to the first power, which is a whole number. And notice here, you don't see an x, but this is actually x to the 0 power sitting here. And 0 is a whole number, right? And so, yes, this is a polynomial. Part B, we're going to say no, right? Because this exponent here is negative, so this is not a polynomial. Sorry, it's not a polynomial function. I was correct there. And this one here, notice it has x in the denominator, right? What we like to do is, instead of writing that in the denominator to see whether it's polynomial, is remove it from the denominator and see what type of exponent we get. Well, if we remove that from the denominator, this exponent is negative. That is not a whole number exponent, and so we're going to say no. In part D, we have y equals. Now, this is a product of two polynomials, right? That's a polynomial there. But if I multiply two polynomials together, does that mean we have a polynomial, right? Well, let's use our for method to distribute everything. We're going to get 3x squared minus 3x plus x minus 1, right? That comes 3x squared comes from there, minus 3x comes from there, plus x comes from that multiplication, and minus 1 comes from there, right? Notice we can combine these like terms. We get 3x squared minus 2x minus 1. Ha ha ha. That's the same one we have there. Similar, it's not the same. So I'm going to undo that. I was getting ahead of myself. But yes, this is to the x to the second power. That's to the first power. That's x to the 0 power. So yes, that is a polynomial function. Let's go to part E here. I have y equals the square root of x plus 1. Remember, we want to see the number on that exponent. And when we have the square root, that's understood to be the 2 as your index. And remember, your index is the denominator of your fraction. So that's x to the 1/2 plus 2. And since this is not a whole number exponent, then this is not a polynomial. All right. Polynomials are actually very cool, are very fun to have because they have good properties that make them good to use in calculus as well. When the highest exponent is 2, you have a quadratic polynomial. When the highest exponent on the polynomial is 3, you have a cubic polynomial. When it's 4, it's quartic. When the highest exponent is 5, it's quintic. And they generally have these shapes here. Again, they're smooth and continuous, but one thing about polynomial functions is that they're defined for all real numbers. That means they're defined from negative infinity to infinity. That's all your real numbers that's possible. That means you can input any real number into that function, and you're going to get an output. Okay, so we'll use polynomial functions when we start talking about calculus, right? And so what we've done so far was we've looked at a bunch of different types of functions. We've reviewed a bunch of different types of functions, right? We reviewed linear functions, exponential functions, logarithmic functions, and then we did power functions and polynomials, right? Basically, our power functions help us come up with polynomial functions. The way we get polynomial functions is we add or subtract power functions that have whole number exponents from each other. And then we can get more complicated functions by doing compositions of functions. All right, and so this gives us a review of many of the functions that we've dealt with or we're going to deal with throughout the semester. All right, this concludes this video. I'll see you during the next one.